Hello, I'm Meni and I'm very excited to present Autarky, which is a joint work with Andrew Baumann and Mark Silberstein. Like it or not, even when viewing this talk, we're sending sensitive information to applications that are hosted on public clouds. Can we trust the cloud? Evidently, we don't need to, by using hardware-protected enclaves. In fact, major cloud providers have already acknowledged support for enclaves, particularly SGX enclaves. SGX offers an isolated user mode environment that can run native x86 code and is available on commodity CPUs. Enclaves offer an extremely small trusted computing base, which includes only the CPU package, while guaranteeing the confidentiality and integrity of their code and data, even against an OS-level adversary. Unfortunately, SGX was shown to be vulnerable to a page fault side channel attack, where the OS can induce spurious page faults to track accessed pages and reveal secrets that depend on the access patterns. For example, previous work used the attack to recover images processed inside the enclave and coined the term control channel attack, since the attacker has full control of the side channel. In fact, most of the infamous attacks that break SGX confidentiality guarantees relies on this attack as a precursor. Why is that? It's because unlike regular side channels, the attacker has full control on the channel and can precisely place the attack without any noise. Next, we're going to present background information regarding the attack. Enclaves rely on the same page table maintained by the OS to manage their virtual to physical mapping. To make sure the OS does not maliciously change this mapping, SGX maintains a reverse page table with the expected enclave mappings. This is inaccessible to the OS, and on every TLB miss, the CPU validates that the OS did not insert spurious mappings. However, SGX does not validate the presence of expected mappings. In fact, we claim there is a missing component in SGX design, which as a result makes it vulnerable to the page fault side channel attack. Without this component, the control channel attack is possible. For example, assume the enclave processes some secret key bit by bit. The loop code is in page 5000, and if the key bit is set, it invokes a function in page 2000. The attacker can mark both pages as non-present. Then, when executing the if statement, the attacker learns that a page fault happened on page 5000. It can resolve the fault and resume enclave execution. When the enclave will execute the mul function, a page fault will happen, this time for page 2000, and the attacker will learn that the secret key bit is equal to 1. Existing software-only mitigations try and detect the attack due to the high frequency of exceptions of any type. This, however, limits usability since it restricts demand paging, may falsely detect attacks, and does not mitigate all the leakage. Another software mitigation relies on provably obfuscating all memory accesses. However, this results in orders of magnitude performance impact. Effectively, software-only mitigations are limited. On the other hand, hardware mitigations rely on private page tables that are maintained by the enclave instead of the OS. Since SGX is entangled with the x86 architecture, supporting private page tables will require major changes to the SGX internals. We propose a new approach with Autarky, a minimal hardware-software co-design that is backward compatible with SGX such that it allows demand paging and does not require major changes in its memory management, while also mitigating the attack by validating the presence of the expected mappings. This is achieved by using self-paging enclaves as discussed next. Autarky gives enclaves power to control all the page faults by forcing the OS to call an enclave page fault handler on every page fault. This will allow enclaves to detect spurious page faults. Furthermore, Autarky relies on an enclave OS cooperative paging, It hides the fault information from the OS and lets enclaves enforce their own paging policies. All this allows the enclaves to support secure demand paging of legitimate page faults. Autarky runtime can be part of a library OS or a smaller SDK and be reused by different applications. It includes an attack detection module, paging policy module, and paging mechanism module. The latter collaborates with the paging module in the OS to resolve legitimate page faults. Let's see Autarky in action. If an attacker clears the present bit with Autarky, the actual faulted address is hidden from the OS, yet it is securely stored in the enclave's memory by the trusted CPU. Furthermore, the OS cannot resume execution of the enclave even if it manages to resolve the fault on its own. Instead, the OS is forced to re-enter the enclave on a new execution stack. Internally, the enclave securely executes a custom fault handler using the faulted address logged inside the enclave. After exiting the fault handler, resuming the enclave is made possible. Note: the enclave is in control of its own page faults, so it can track the expected mapping presence and detect the attack, which means the OS is no longer in control of the channel, and therefore the original attack that required millions of page faults is no longer possible. So removing the control reduces the leakage tremendously. Autarky maintains SGX support for demand paging when legitimate page faults does occur. On a fault, the enclave handler will be invoked and can collaborate with the OS to resolve the fault. While the OS is unaware of the faulted address, naively passing it during the cooperative paging would still leak. So, can the enclave do something else? Yes, enclave paging policy is part of the runtime and can therefore control what requests are made to the OS. Which policies can be used to reduce the leakage? First, let's consider existing state-of-the-art software mitigations that put a limit on the rate of exceptions. Autarky can also use this approach to bound the leakage. However, since the enclave is now in control, it can consider only page faults and not any type of exception. It can work with unmodified binaries, including those that rely on JIT runtimes. It is enforced by the architecture and does not rely on potentially unavailable microarchitectural components, such as transactional memory. And our evaluations show it results in an extremely low overhead. While this policy may still leak access pages, other policies can hide it, yet with a slightly higher performance cost. One notable example is Oblivious RAM, or ORAM in short, a well-established cryptographic primitive that was used by prior works to provably obfuscate the distribution of all of memory accesses. These works reported a substantial performance cost for using ORAM. Unlike them, Autarky is orders of magnitude faster, since it invokes ORAM only for paging and not on every memory access. And we refer you to our paper for more details on how Autarky supports ORAM. Considering some applications do not need oblivious paging for all of their pages, we propose a novel policy we call page clusters, where non-sensitive pages can use naive paging and not impact performance, while sensitive pages can be placed into clusters. Cooperative paging with the OS works for all the pages in the cluster, so upon a fault to some page, all the cluster will be fetched together. Since the actual faulted address is hidden from the OS by Autarky, the attacker cannot learn which page had actually faulted. One use case we describe in the paper is for a spelling server containing dictionaries for different languages. The server receives requests with a word and a language and reports whether it is correctly spelled. Putting each dictionary in a cluster, the attacker may learn the victim accessed a certain dictionary but not which word was queried, which may be acceptable for some applications' threat model. Similarly, Code libraries can be clustered as well, such that the attacker cannot learn which function or even internal control flow statement was executed. Autarky supports both SGX version 1 and version 2 paging mechanisms. Also, Autarky eliminates leakage due to the accessed and dirty bits being updated in the page table with practical modifications, and it proposes practical optimizations to remove overhead due to costly enclave costing to the OS that happens on every page fault. For more details on this, please refer to the paper. Finally, we present the evaluation results of Autarky. We ran memcached key value server configured to store more than 2 times the available enclave memory on our system, so legitimate paging occurs. We issued random 1 kilobyte GET requests and measured the throughput for different distributions. Ordered by SKU levels from left to right, the baseline is an unsecured vanilla SGX, and we can see the throughput increases with hotter distributions since less paging occurs. Using rate limiting policy, there is only 30% lower throughput for uniform requests, whereas the hottest distribution results only in 7% lower throughput. This overhead is mostly due to costly enclave crossings to the OS, and we show in the paper how it can be optimized to be much lower. For the page cluster policy, we use 10 page clusters, making paging more secure, but also reduces throughput, since each page fault must fetch and potentially evict 10 pages together. Finally, using ORAM with the hottest distribution results only in 60% lower throughput. Interestingly, it is better than the page cluster policy, since ORAM has a better cache utilization, so less overall page faults occur. To conclude, Autarky mitigates the control channel attack with practical modification to the architecture, while also maintaining backward compatibility with SGX design. Finally, the control channel attack is not unique to SGX enclaves, and we believe Autarky can be retrofitted to protect other enclave environments similarly. Thank you for your time.